Good afternoon, my name's Tom Hardy and I'm a lead transmission engineer at SMT, and I'm going to go through SMT's NVH troubleshooting capabilities with you today. So the agenda for today is go through the NVH capabilities. So I'll start with methodologies, go through the team, as well as past project experience. I'll then go through some advanced analysis examples, followed by case studies, and then a summary of the advantages of SMT's approach. SMT's NVH capabilities. The SMT team has delivered numerous NVH projects successfully for a range of clients, including luxury, European, US, Japanese vehicle manufacturers, and we're recognized as a leader in the Powertrain NVH optimization, including the HEV NVH application, where gearbox and motor interactions are additionally required. We have developed full test, analysis, simulation capabilities with our Measure, MASTA and DRIVA softwares, which can be used to identify root causes of NVH issues, as well as validating design optimization solutions. And we're continually developing innovative technology to improve our simulation and optimization capabilities. SMT has established a full design process for optimum NVH performance and NVH troubleshooting. We have considerable experiences and best practices built up over many years with internal research and development projects, customer consultation projects, as well as customer validation exercises using SMT's products. So I'll go through the main methodology that we apply in a project. So this starts with test data analysis and test data acquisition. So we will measure NVH data using accelerometers and microphones. Contact patterns are also recommended where possible. In parallel, we'll be building a MASTA model, so we can correlate our simulation results with the test data, focusing on contact patterns and vibration response. We will also look to analyze the test data. So we need to identify the sources of the different orders, measure and MASTA integrate well here, so you can export the orders from MASTA into Measure very easily. We can look for critical frequencies, check if there's resonances, check for critical speeds or loads that are relevant to the NVH problem, and this feeds into the identification of the root causes. So we will start to look at and simulate the system behavior. So deflections under load, looking to predict gear misalignments. We will examine the gear geometry. Is a further optimization of the gear geometry possible? Then we'll simulate TE and other excitations and compare them to best practices, followed by analysis of the transfer path and system response. So from this we will identify a number of causes of the NVH problem, and then we will, as part of the optimization phase, look to improve the system to remedy these problems identified. And that will be an iterative process where we try various combinations and options to see what we can get, how much we can reduce NVH. Then we move on to the validation of the solutions with manufacture of prototypes and then testing of the prototypes. And typically we'll meet the targets with the first prototypes. It's important to include to use a high fidelity model to accurately simulate the NVH response. So for this we use a fully integrated system model, including the up and downstream soft stiffnesses and inertias. Sometimes we model the half shafts within MASTA as well. Also sometimes the chassis is included as a full FE model if that is deemed to be a significant part of the problem. Casings, planet carriers and complex shafts all need to be modelled in full FE to accurately simulate deflection and mode shapes, as well as the gear blanks. We can do accurate simulation of the mesh performance using advanced LTCA. And then we look at the response of the casing or the chassis. Okay, so in a bit more detail, we start off with the system deflection to predict the mesh misalignments. This is then used in the loaded tooth contact analysis calculation to predict transmission error and shuttling forces. Then we perform a frequency domain analysis and use the dynamic compliance of the gear pair, which is excited by the TE to give a dynamic mesh force, which then propagates through the system to the responder on the case, and we can predict accelerations or sound powers of the case. In addition, you can also examine the gear to casing force response function. As part of our modelling, we look at a number of different sources of noise or excitations. So the most common one is transmission error. We'll simulate the transmission error as you roll through the gear meshes and you get your peak-to-peak TE, but the actual excitation is calculated by the FFT of that to break down the frequency at the tooth passing frequency, the first order, and then its higher order components. It's important to include bias. So this can be either designed bias or bias that's naturally formed as part of the manufacturing process and how it impacts your transmission error or the shuttling force. Shuttling force is another excitation that can be quite significant and is worth including in your simulations. So a shuttling force is how the position of the load varies on a helical gear as you roll through the mesh. The centre of force will move back and forth depending on the number of teeth in contact. Third excitation can be sidebands. So in this case you will need to use MASTA's advanced system deflection module. And this is a modulation of either shuttling force or transmission error and produces orders either side of the tooth passing frequency. So this can be due to manufacturing variation or asymmetrical stiffness of the components. Then we have motor and gearbox excitations and interactions. So you have torque ripple, which can be used to excite the system. You have to extract the torque ripple and force variation from an external package, and that will then be used to excite the system. The advantage of MASTA is that you can also look the other way. You can look at how the gearbox excitations propagate through the motor system. And then finally you can look at once per revolution excitations due to unbalance or run out of shafts. You can also use MASTA's DRIVA analysis. This is a time domain analysis, full multi-body dynamics simulation, which can be used to simulate Rattle type problems. So this is when lightly loaded gears can be excited by, for instance, torque variation from your engine, and then rattle causing broadband noise. SMT are considered to be world leader and pioneers of NVH technologies and solution innovation. We have a large specialist NVH team with substantial experience from external consulting and internal research projects. So we have a large dedicated team with around 20 years experience, who delivered numerous NVH projects in global markets. We're obviously involved in the development of state-of-the-art NVH analysis software, MASTA, DRIVA, as well as Measure. Also innovated various design and manufacturing solutions for low NVH. We've been involved with various OEMs and tier 1 suppliers, helping to build knowledge of within their NVH teams and departments. As we have sold over 250 NVH licenses globally, and as part of the support of MASTA, we are able to always enhance our knowledge and improve our understanding of NVH best practices. Here is a list of our NVH past project experience. So in the early 2000s we were working in looking at rear axles, NVH optimization. We've looked at, we've designed a complete transmission, manual transmission, which had excellent NVH performance, even at the first prototypes. Worked with tier 1 suppliers with knowledge transfer projects, and they have adopted MASTA as well as our NVH optimization methodologies. Worked on a number of NVH troubleshooting projects over the years. So in this example it's an EV bus, but we've also worked on HEVs, SUVs, done gear blank tuning for various Western OEMs. We have performed NVH optimization in electric rail drivetrains, designed EV gearboxes with input speeds up to 15,000 RPM and with really good NVH performance shown in testing. Multiple projects for European Tier 1 transmission suppliers. Helped with a novel e-axle in the Japanese market, along with ongoing NVH optimization for EV applications. Most of the projects are able to achieve the targets with the first prototypes, and a small number require further optimization. Timescale wise, as an example for the complex HEV, the root cause analysis design optimization were completed in 12 weeks. And we were able to tailor the solutions to meet the manufacturing requirements of the client, so that to ensure that the manufactured gearboxes are able to meet the performance, the predicted performance. I will now talk about the case studies. The first case study is NVH optimization in an electric bus. The challenges in this project were the layout meant the support of the first stage gears was not optimal, so misalignments were compromised, as well as the support of the motor shaft. So they had problems with gear wine associated with the first stage and motor. So the optimization focused on improving the system stiffness and the support of the motor shaft. We optimized gear macro and micro geometry, and there was also some resonant panels on the case. So you can see the improvements we achieved. Before, they had a number of orders with significant noise, and then after we optimized it, the contribution of these orders was much reduced. This is an example of an NVH optimization in an HEV, so SUV application. It has a compound planetary with 2 electric motors, and then transfer gear set to power the differential. They had noise associated with compound planetary, which was the largest contribution of the noise, but also noise associated with the transfer gear set. The problems were associated with, again, system stiffness. So we optimized the support of the transfer gear set pinion support, as well as the planetary gear support. We optimized the macro and micro geometry of the planetary gear sets and transfer gear sets. There was an additional problem associated with high wear on one of the bearing races, the needle roller bearing race, which again was associated with the system stiffness. So the bearing had high misalignment and was skidding. Finally, we optimized the support of the sun gears so that the excitation was decoupled from the motors as much as possible. And you can see we have had significant improvement on the transfer gear set and planetary gear set orders. And if we look at the order cuts, the noise in this region was the most significant problem, both in terms of how far above the target it was, but also due to the frequency. It was around 2.5 kilohertz, so in this region your ear is very sensitive to the noise. So we focused optimization on this area in particular to get it down as much as possible, and you can see the end result is it's well below the target. These relate to a number of gear blank optimization projects we performed for customers. So you can see we use scripting to alter the shape of thickness of the gear blank, and then we can run a number of different geometries to see the effect on the sound power. You can get up to 10 dB reduction in the sound power. This project is a design of an EV gearbox. This is it's been a very successful EV gearbox. One of the main challenges with this was the high installation angle that made getting oil to all the gears challenging. The end result, it was a very high power density and had exceptional NVH performance, meeting the NVH targets first time. This is a NVH optimization in a electric train. This is an example where misalignment, excitation or shuttling forces were very important, so much so that this prevented us from using helical gears, although we were able to reduce TE, the increase in misalignment excitation, particularly with the sensitivity to the misalignment excitation, meant that the overall response was worse with helical gears. And this was backed up with the client's pre-project experience, where they had tested helical gears and found that the overall response was worse. So we restricted to optimizing the gears to spur gears. So we went to high contact ratio gears on one of the stages. The other stage, it wasn't possible to get a contact ratio above 2, so we just maximised the contact ratio and optimised the microgeometry, and we were able to get significant reductions in the noise. Here we have a project where we were supporting an e-axle design for an OEM, so the dual motor for a passenger car. We were responsible for optimizing the gears. We were able to produce good results using the design space search functionality. And finally, I'll just give a quick summary of the advantages of SMT's NVH approach. So we have a very good track record in NVH optimization or designing transmissions with low noise. Prototypes will achieve targets with the minimum number of iterations, as we have exceptional NVH software packages, specialist and NVH equipment, systematic approach with extensive experience. We can achieve these in short timescales with minimum costs due to our methodologies, tools, and team experience. And we do provide knowledge transfer to the client NVH teams with training at the end of the project. This is at an additional cost, which is available. Thank you for listening.